Okay, so there's many things that I have to do, which um, usually I gonna get confused. Okay, anyway, so the Gauss law is this. The electric field, well, not electric field. Oh, this is called the electric flux. So the symbol is this, which is a capital letter of phi, phi, and some of you might pronounce it phi, but I don't know what's the correct way of pronouncing. So I call it phi. It's a big phi and subscript e. This is called electric flux. Okay. By definition, electric flux is the dot product between electric field and area. It's a really strange way of saying because at this point, the area we thought is it should be a scalar. It doesn't have a direction, so how can it be vector? Um, but it turns out that you can define the area to be a vector. So it's an area times the electric field that gives you the electric flux. Okay, that's what we call phi of E. So how do we think about this? For the area here is the area that you imagine. So for example, if you have some electric field in some region, maybe pointing this way, right? So electric field pointing like this. And then the area is something like this. So imagine that you take a piece of paper and then you put the paper in the the area where you have electric field. And if you imagine electric field to be some kind of arrow, I mean you cannot see it, right? But imagine that you can see it and imagine that it's actually an arrow pointing in whatever direction it's pointing. You can take the piece of paper and then you can see how many arrows of electric field is piercing through the paper, right? And this area is the area that I talk about in this expression here. So it's the area of the paper that you imagine that is there. So what is the direction of the area? Well, the direction of the area, which is the area vector, is the one perpendicular to the paper itself. Okay, so definition of vector A is a vector pointing perpendicular to the area. Okay, it's a vector pointing perpendicular to the area. And the magnitude is the area itself. Okay, and this is why I don't like online lecturing because I have something that I want ready to show you in person, but I cannot do that. But anyway, just imagine that you have a piece of paper, right? And the vector, the area vector is the one pointing perpendicular to that paper. So if you rotate the paper to point in a different way, then the area vector will also point in a different way, right? So it doesn't matter which way your piece of paper is, it's always going to be pointing perpendicular. And the magnitude of the area vector is just the area of your paper like this. Okay, so if you take a piece of paper which is like 1 centimeter by 1 centimeter, the magnitude of the area is just 1 square centimeter. So that's going to be the magnitude of your vector A. Okay, so now that you know what is the vector A, you can calculate the dot product between electric field and the area vector A. So that's going to be just the electric field magnitude times the area magnitude times cosine of the angle between them. Okay, so if you, for example, have the situation where electric field is pointing up in this case, right? The flux, electric flux, is this electric field multiplied by this area multiplied by cosine of the angle between them. That's the definition of the electric flux. Okay, so there will be the case where electric flux is zero. For example, if you have electric field pointing up, 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 up like this, and you take a piece of paper which is in this orientation, so the area vector is pointing that way, sideways like this. Right. So just take a piece of paper and then you just put it vertically. So the area vector gonna point perpendicular to the surface or the paper, which is perpendicular to the electric field. Right. So in this case, the flux is zero because the angle between the area and the electric field is 90 degrees. So the flux is zero. Okay. So in other words, if you think about this situation, and the flux is kind of like counting how many electric field arrow piercing through the paper. In this case, because all the electric field gonna point up, so it's not gonna pierce to the paper at all because the paper is also vertical, right? So that's why the electric flux is zero, right? So electric flux depends on the direction or the orientation of your piece of paper and the electric field, right? So if they are perpendicular, like A and E are perpendicular, then the flux is zero, right? If you have the other case, which is an extreme case, where the electric field are all pointing up, like this, up, 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 and then you put the piece of paper horizontally, like this. So the vector A is also pointing up, right? In this case, you have kind of maximum possible electric flux because cosine of 0 degrees of is 1, right? So electric flux is just E times A in this case, right? So what does the Gauss law tells you? Well, the Gauss law says something like this. If you have charges in some area, Q1, Q2, Q3, and it can have, positive charge or negative charge, whatever, right? So if you have like some charges here, and if you imagine that you cover this whole area by a closed surface, right? So it's kind of like a balloon which encapsulate the whole area. So Gauss' law tells us that the total flux phi of E total. Total means the flux across the surface of this closed surface. The total flux is equal to the sum of all the charge inside divided by some constant which we call epsilon 0 here. So don't worry about what epsilon 0 exactly is. At this point, just think about it as some kind of constant, which I will talk about later. So this is the Gauss law. Again, it's a really strange law because sometimes we don't know how to use it. Okay, so again, let me try to explain this one more time, right? So imagine that you have a sphere, maybe a balloon, right? And this balloon has the surface area, right? Because it's a balloon. And then let's say inside the balloon you have some charge, or let's consider just one charge, Q1 here. Right? It doesn't matter where it is as long as it's inside the balloon. Right? So if we calculate the total flux across all the surface, I don't know how to draw it, like all the surface of this balloon, you're gonna have E, phi of E total equal to the charge inside, which is plus Q divided by epsilon 0. Always. So what it means is that, let's say the charge is here inside the balloon, right? And we want to calculate the total flux. So what do? Well, we need to look at one particular area on the surface of the balloon. And then we have to see what is the electric field at this point. So it might be electric field here. Right. So how to calculate the flux is this electric field times this area. Right. So that's going to be the flux through this area. But that's not the whole balloon. So we need to keep working. So we need to pick another surface, and then we need to see, okay, what is the electric field here? And then what is the area here? So electric field times this area, that's going to give you the flux through this small area. And still, that's not the end, right? Because we still have a lot of area to calculate. So you just keep doing this until you cover the whole area of the balloon. So once you add up all of that tiny flux all together, that's going to be the total flux. So the amazing thing about Gauss' law is that it doesn't really matter where Q1 is. As long as it's inside the balloon, the total flux is always given by this value. That means if I have Q1, but now I move Q1 to a different place, maybe a little bit closer to that side of the balloon, right? I can calculate the flux again, but I mean, it's going to be different, right? Because when you move the charge, then the electric field will point in a different direction. So in this case, if I want to know the electric flux at this point, I need to calculate the electric field from this charge, which is going to point this way, and then multiply by this area. And then I have to do the same thing here, here, here. And then here, which has a really strong electric field because it's a lot closer to the charge, right? But if you do this and then you add up the flux, all the surface, you still get this value, no matter where Q1 is, as long as Q1 is inside this balloon, right? So if Q1 is outside the balloon, let's say I move Q1 to be outside the balloon, like here, I put Q1 here, then the total flux through this balloon will be 0 because there's no charge inside the balloon, right? So this is what Gauss' law tells us, that the total flux through this balloon, and the balloon doesn't have to be spherical, it can be any shape, right? As long as it's a closed shape, so that you can define what's inside the balloon and what's outside, right? So it has to be a closed shape. It doesn't have to be spherical, right? If you have the charge inside the balloon to be equal to 0, so Q equal to 0, then the flux total on this surface will also be 0. So in a sense, Gauss' law tells us that in order to tell whether the surface contains any charge or not, you don't need to look inside the balloon. You just look at the surface of the balloon, right, and calculate the flux, right? If the flux is 0, then inside the balloon, you have no charge, Q equal to 0. So that's what Gauss law means. And it's a little bit abstract because, again, electric flux is something that you cannot, well, you cannot see electric field, not to mention electric flux, right? So it's a little bit strange, but there is some use in using the Gauss law. So one thing that I will do is to apply it to the question that we did earlier. So I need to set up. So the question we did earlier is this. So imagine that we have an infinitely long wire. Infinite wire with charge density given by lambda. Okay. So this is charge density. Exactly that we did before the break. So this is the charge density. And we want to know the electric field at this point, which is a distance r away from the wire. And then again, this is infinitely long. So it goes to infinity in both directions. We want to find the electric field at this point. Remember how we did it last time? We have to integrate it, right? And then we need to set the limit of the length of the wire going to infinity, right? But we're going to redo this using the Gauss law. So again, what does the Gauss law say? Gauss law says that the electric flux at the surface of any closed surface is equal to the charge inside divided by this constant epsilon 0. And again, the important point is that it can be any surface, doesn't have to be spherical, right? So you can choose the surface which is suitable to your problem. And in this case, I have infinitely long wire. So the surface that I choose should have kind of the same symmetry of this wire. And the surface I will choose is actually going to be a cylinder. So a cylindrical surface. Like this. Okay, so imagine that you have a balloon which is weirdly shaped like a cylinder like this. And then you put the balloon here. And then you put it such that the wall of the cylinder is exactly the point that you want to calculate the electric field. Right. So this is an imaginary cylinder. So I can say it's a cylinder shaped imaginary balloon, right, that you kind of dream about, right? And so this cylinder shaped balloon or any shape, we have a name which is called the Gaussian surface. Actually, what it means is that it's a surface that we can apply Gauss law to. Okay, so in the example before, the Gaussian surface is a spherical surface, but in this case, it's a cylindrical surface. So it's a cylinder. And the reason why we choose it like this is that we know from the symmetry that the electric field will point perpendicular to the wire. So it's going to point out in every direction, right? So it's a little bit hard to draw, but you get what I hope you get what I'm trying to say here. Right? So I'm trying to draw like 3 dimensions here. So the electric field is pointing away from the wire in every direction, right? It's pointing in a perpendicular way. So the Gaussian surface is cylinder, right? So that means for the lid of the cylinder, this surface, there will be no flux, right? No electric flux because the electric field will point perpendicular, right? So if your electric field and the surface, the area is pointing in this way, then there's no electric flux. Okay, so I can write that the lid here, the surface here, the lid has no electric flux, and the lid here the lid here has no electric flux, right? So the only non-zero flux is going through this area, which is the wall of the cylinder. Okay? So the wall of the cylinder gives you electric flux, which is non-zero, because electric field and area along the wall, they point in the same direction. Right? So this takes some imagination of like how the geometry works. So think about this slowly, how this works. And I will assume that the length of the cylinder that I drew here is small l, right? So I would write down the Gauss law and then I will try to use it to calculate. So the Gauss law says that the total flux is equal to the total charge inside the balloon divided by this constant, epsilon 0, right? So if I choose the balloon, which is a cylinder-shaped balloon, to be a length L, that means the wire inside the balloon, inside this cylinder balloon, is also a wire of length L, right? Because anything else is outside the balloon, we don't count that. We only count the charge inside the balloon, which is the wire of this length. Okay, so Q inside is just L times the charge density, right? That's the amount of charge inside the cylinder. That's Q inside, divided by epsilon 0. Okay, so the right-hand side of this equation is all taken care of because that's just counting how much charge you have inside this cylinder. But what about the left-hand side? Well, again, due to the symmetry of the problem, the electric field is pointing perpendicular to the wall at every point on the wall. And because I set up the cylinder such that the wall, no matter which point you pick, is the same distance from the wire, right? That's how a cylinder works, right? So the total electric flux is just the electric field times the area of the wall. And what is the area of the wall? The area of the wall is just 2 pi r, which is the circumference of the lid, times the length of the cylinder, which is L, like this, or small l, like this. Okay, so this is the surface area of the wall of the cylinder, 2 pi r times L. And the good thing is small l cancel out on both sides. So the electric field now is simply lambda divided by 2 pi r times epsilon 0, like this. So electric flux, so one of you asked, what is electric flux exactly? So electric flux is just how much electric field going through the area. So one way to think of this is imagine that you have a river, right? You have a river, and the river has water flowing, let's say to the right. And the electric flux is how much water you have going through a certain area. But instead of water flowing, we are talking about the electric field. So the flux is like how much electric field is flowing through a particular area. So that's kind of, I think, the easiest way to think about the flux. Okay, so I hope this picture helps a little bit, right? So think about the electric field is kind of like, some kind of water flowing out from the charge, right? If you have a charge here, you have electric field pointing out. So you can think of this as, like some kind of, water or something flowing out from this point. And the flux is, let's say you take some area here, and you see like how much water is flowing through that area, right? So imagine in this picture, if you have a river like this, and you put the paper horizontally, right? Then you're not gonna feel anything because the water will just go through the paper like this. So you have no flux because there's no water going through that paper, right? So you can see like how the orientation of the paper gives you different amount of flux, right? So it's kind of something similar here. Okay, anyway, so this is the calculation of the electric field, which is done now. And then I'm going to show you the previous page later. Let me finish this. So how do we compare this to the result that we got earlier? Well, one thing I didn't tell you that the K value in Coulomb's law is actually related to epsilon here in this way. 1 over 4 pi epsilon 0. Okay, so in this case, what we can do is we can just convert this back to K, which is 2K divided by R times lambda here, which is what we got earlier. Okay, so I'm going a little bit fast here. I apologize. So you probably need to read the lecture or watch the lecture again. But what we got here is the electric field using Gauss' law. And it's the same result that we got here, right? But it's a lot easier because there's no integration going on. You just draw a nice picture and then you say, okay, the flux is equal to the charge inside. Okay, so this is the situation where Gauss' law is useful, but you can see the limitation right away because like if you don't have this kind of symmetry, then Gauss' law is not going to help much. Anyway, I will continue talking about this next time. So I'm a little bit over the time here. So I think I will stop at this point and then I will see you next week. Okay? You want to see this page? Which page do you want to see? Is this the one? Yes? Okay, good. Yeah, so I mean, if you don't have anything, then you can leave the session. And if you have something, you can ask now because, I mean, conceptually, this is probably the hardest thing that you can encounter in this course. All right. Okay, well, if you don't have anything, well, next time I'm going to talk a little bit more about Gauss' law, but I will stop here today. All right, so take care, everyone. I will see you next week then.